All right, let's get right into it. Today, we're going to learn the language of movement. This is the fundamental way scientists describe how literally everything in the universe moves, whether it's an apple falling from a tree or an entire galaxy hurtling through space. We're going to break down motion in a straight line, and we'll start with a question that's, well, trickier than it sounds.
So let me ask you, are you moving right now? And you're probably thinking, no, of course not, I'm sitting still. But think about it. You're on a planet that's spinning on its axis, right? And that planet is orbiting the sun, and that sun is flying through the Milky Way galaxy. So are you moving? The answer, it turns out, really depends on your point of view, on your frame of reference. Motion is always relative. So, to talk about motion in a way that makes sense, we first need to learn its basic alphabet. You'll see that pretty much every physical thing we can measure gets described in one of two ways. And understanding this difference, well, it's the foundation for everything else we're going to talk about. Okay, first up, we have what are called scalar quantities. The best way to think about these is that they're just simple, straightforward numbers. That's it. If I tell you an object has a mass of 5 kilograms, the story's over. You have all the information you need. The magnitude, the 5 kilograms, is the whole deal. You never ask, 5 kilograms in which direction, right? It just doesn't make sense.
But then, you have vector quantities, and these are a bit more demanding. They're needier. A vector needs two things to make sense: a magnitude and a direction. If I just told you, I walked 5 meters, you'd be left hanging. But if I say, I walked 5 meters east, now you've got the complete picture. That's a vector. So, this is the absolute key takeaway. Scalar, just a number. How much? Vector, a number and a direction. How much and which way? It seems like a small detail, but trust me, this little difference completely changes how we talk about a journey.
Okay, so we've got our alphabet, scalars and vectors. Now we can start building our first real words to describe motion. And we'll start with two ideas that sound really similar but are totally different: the actual path you take versus where you end up.
And this image just lays it out so perfectly. Imagine you walk from point A to point B, but you take that long, winding, curved path. The total length of every single step you took along that path, that's the distance. But the displacement, that's just the shortest straight-line path from where you started, A, to where you finished, B. It only cares about the start and end points.
This table breaks it down even more. Notice distance is a scalar. It's just a number, like miles on your car's odometer. And it's always positive, right? Because every step adds out. Displacement, though, that's our first vector. It's got a direction. And because of that, it can be positive, negative, or even zero. Think about it. If you walk all the way around the block and end up right back on your doorstep, you've walked a pretty big distance, but your displacement is zero.
Here's a great example to really nail this down. This boy walks 4 kilometers east, and then he takes a left and walks 3 kilometers north. The total distance he traveled is easy, right? You just add it up. 4 plus 3 is 7 kilometers. But his displacement, his final position compared to where he started, is that straight line arrow from start to finish, and that's only 5 kilometers to the northeast. See, two different ideas, two totally different numbers.
All right, we've got our words down, distance and displacement. So now we can start putting them together with time to make more useful phrases that tell us how fast something is actually moving.
And here's another one of those classic pairs that can get confusing. Speed is just how fast you're covering ground. It's based on distance, so it's a scalar. When your car's speedometer says 60 miles an hour, that's your speed. But velocity is the rate of your displacement. Since displacement is a vector, velocity is a vector too. So for velocity, you'd have to say 60 miles an hour, north. One tells you how fast, the other tells you how fast and in what direction.
Now this is where it gets really interesting. Look at this object moving in a circle. It could be moving at a perfectly constant speed, let's say 10 meters per second, the whole way around. But because its direction is constantly changing, right? First it's going up, then left, then down. Its velocity is also constantly changing. So you can have a constant speed, but a changing velocity at the same exact time.
And this quote just nails it. Imagine that object does one full lap. It ends up exactly where it started. Its total displacement is 0. So its average velocity for that whole lap is 0. But it was moving the whole time, wasn't it? So its average speed is definitely not 0. See the difference?
So, we've talked about where you are and how fast you're going. But what about when that changes? What about when you speed up, or slow down, or turn? This brings us to the grammar of motion, acceleration. It's all about the change.
So acceleration is just the rate of change of velocity. And here's the kicker. Since velocity is a vector, acceleration has to be a vector too. This is so important. It means you are accelerating if you speed up, you're accelerating if you slow down, and you're accelerating if you just change your direction. That car going in a circle at a constant speed, yep, it's accelerating the whole time because its velocity is always changing.
Now what about when your velocity is decreasing? You know, like when a car hits the brakes. We just say the acceleration is negative. The more common word you'll hear is deceleration. You might also see an old-fashioned term in some textbooks, retardation. It all means the same thing. You're accelerating in the opposite direction of your motion.
In one of the examples from our source material, a car hits the brakes, and its acceleration is -5 meters per second squared. Now, that little negative sign is incredibly important. It's not just a detail, it's telling you a story. It's telling you that the push of acceleration is happening in the opposite direction to where the car was traveling.
We've learned the alphabet, some words, and even the grammar. So now let's learn how to read the entire story of a journey in a single glance. And honestly, the most powerful way to do that is with graphs.
Okay, let's see how this works on a displacement versus time graph. On the left, we have an object that's just sitting still. As time ticks by, its position, or displacement, doesn't change at all. So you get this flat, horizontal line, a slope of 0. But look at the graph on the right. Here, the object is moving with a uniform or constant velocity. Its displacement increases steadily with time, giving us a straight, sloped line. And here's the really cool part. The slope, how steep that line is, that is the velocity. A flat slope is 0 velocity. A steeper slope means a faster velocity. And this graph is a fantastic way to see how direction works. So you have a ball moving toward a wall, it hits it, and then it bounces back. Look at the first part of the graph. It has a positive slope because the ball's displacement from its start is increasing. Then, bam! It hits the wall and starts coming back. And now look, the slope becomes negative because its displacement is now decreasing. It's getting closer to where it started. The slope tells you the whole story. So let's just boil it all down. These are kind of the 3 golden rules for reading these motion stories. Rule 1, the slope of a displacement time graph gives you the velocity. Rule 2, building on that, the slope of a velocity time graph gives you the acceleration. And rule 3, this one is pretty mind-blowing, the area under a velocity time graph actually gives you the total displacement. With these 3 rules, you can decode just about any story of motion you see.
So we've seen how a change in position over time gives us velocity, and a change in velocity over time gives us acceleration. It kind of leaves you with one last question to chew on, doesn't it? If you're in a car and the driver suddenly slams on the gas, you feel that push backward, right? That's acceleration. But what about that initial jerk you feel? What do you call a change in acceleration? Well, that's a story for another time. Thanks for joining me.